kind of bring a couple of the concepts that we've been talking about together. Kind of cool demo, I like it. We're also then going to we're going to move pretty quickly through some of the remaining material just because I don't know yet if we're going to have a snow day or tomorrow, okay? If we have a snow day tomorrow, I want to have to use as little class time on Monday, finishing this chapter as possible so that you have time to work on your midterm packet. So we're going to get through as far on chapter 8 today as we can. Then if we do have class tomorrow, you'll just have extra practice time, okay? But let's start with the demo. Okay, so first of all, does anyone know why we use soap when we wash instead of just washing with water? Chris? It does what? Okay, so it grabs onto the oil and dirt. Okay, so that we're going to talk about specifically what it does, but yes, soap helps remove some of the things that water doesn't. When you ladies or gentlemen, some of you, when you paint your fingernails, do you use water to take off nail polish? No, why not? Because it doesn't work. Okay, what do you use? Katie. Nail polish remover. Does anyone know what nail polish remover is, Chris? It's acetone. Yep. So acetone is a molecule that will remove nail polish. So now we're going to talk about why some things will remove other things and sometimes they don't. It has to do with a concept called, well, it's not a concept, but it's the same scientists use, like dissolves like. And when we talk about dissolving, that's going to break apart or remove, okay, make it disappear. And the like we are referring to in this case has to do with the molecule itself. We are talking about polarity. So in our last class, we talked about how some molecules are polar and some are not. Polarity is very important because under this concept of like dissolves like, only polar molecules will dissolve other polar things. And nonpolar will dissolve nonpolar. So let's look at some of these things in action. So first of all, let's see if you remember this from biology or from your studies yesterday. Water, commonly known as the universal solvent. That implies that it can dissolve anything, but it can't. What type of molecule is water? Polar or nonpolar? Polar. See these unshared electron pairs? They are not like the other things. So water is a polar molecule. Therefore, it can only dissolve other polar substances. Here's what I mean. Here is water. We all know that salt will dissolve in water. Guess what? Salt is a very polar substance. As a matter of fact, if you take the electronegativity values of sodium and chlorine, which are on the top of your periodic table, you will find that it has a very large difference, which means it is a polar bond. Okay, so it is a polar molecule. And if I swirl it around long enough, it will all dissolve. Okay, now it's kind of bubbly and cloudy, but there is no salt on the bottom of this. I'm videoing this, so no salt. Okay, but what about something like styrofoam? Styrofoam is made of molecules. Does styrofoam dissolve in water? Doesn't fit. It definitely won't dissolve if it won't fit. You put styrofoam in there, it better not dissolve because a lot of wraps are made out of styrofoam. Okay, so styrofoam will last forever in water, even salt water. Okay, however, let's take a look at another common substance called acetone. Who wants to be my sniff tester? Not in some way. You know what acetone smells like? Wafting. Look at that, you guys can probably smell it, right? Excellent wafting technique. Okay, so acetone, we're now going to decide if acetone is polar or non-polar. It smells, but it is not dangerous. You use it, well, not everyone, but people use it all the time to clean their nails. Okay, I can put my finger in there. Obviously, I'm not going to lick it. Feels a little cold. That's just evaporation. Let's put some salt into this liquid. We would think our liquid would dissolve our salt. Okay, we're going to swirl it up. Okay, take a look at the bottom there. Did our salt dissolve? No, you can clearly see a pile of salt in there. It's not even cloudy. Why do we think the salt didn't dissolve? Nick? One of them's polar, one of them's non-polar, but salt dissolves in water. So which one is polar? The salt is polar. Acetone is non-polar. The styrofoam did not dissolve in the water. This is the fun part. Ready? Now remember, I put my finger in this. It didn't hurt it at all. It takes a second. Oh, just splashed on my phone. That's not good. It is dissolving the styrofoam. What kind of molecule do you think styrofoam is? Non-polar molecule. That's really polar. Lo and behold. Look, I got some glue left. Did you know that there's glue in styrofoam? Yes, glue holds all those little particles together. What kind of molecule do you think makes up the styrofoam? Polar. Polar, because it did not dissolve in the styrofoam. I'm going to pass it around. It's kind of fun. It's like so funny. It feels cold because the acetone is evaporating. Don't eat it. Okay, so pass it around. Let everyone feel that. That is the glue that makes up styrofoam. Okay, so that brings us back to this. Polar can only dissolve polar. Your skin has oils on it. That's where your dirt is. And like Chris said, we use soap, which is a non-polar substance, in order to break that grease apart and pull off that dirt. We have to use acetone on nail polish because nail polish is non-polar and will not come off water. Okay, so that means that you can predict for any molecule if it will dissolve in water or not by its Lewis dot shape. So here is a common household cleaner, ammonia, NH3. Will this molecule dissolve in water?
No. Yes. Yes.
Well, what do we need to, what does it need to be in order to dissolve in water? It has to be polar. Is this polar? Yes, remember, an unshared pair automatically makes it polar because we have 3 hydrogens and something different. So yes, this will dissolve in water. Polar dissolves in polar. One last example, because a common misconception about oil and water is that they separate because they have different densities. That is not the case. As we mentioned, we use soap to take the oils off of our skin. Oil and water have different polarities. Oil is non-polar, water is polar, and they will separate. I could shake this up.
So it's not because
It's not because of different densities. because oil is non-polar and water is polar. If they were both polar with different densities and I shook them up, they would mix together and not separate. Okay? But they stay separated. Now some bubbles of water filled in.
I always thought.
Nope, with these particular substances, it's polarity. All right. That ends our little demo. Oh, I didn't show that on the screen there. Okay. Talked about polarity at two different times in this packet. One time we were talking about it in relation to bonds, and the other time in relation to molecules. Okay, so let's just do a quick review. A bond polarity only refers to the connection between two atoms. Okay, we're not looking at the entire molecule. So if I gave you carbon and fluorine, and I asked you if what bond type it was it polar, non-polar, etc., what would you need to do to figure that out? Does anyone remember? Okay. For a bond, we use electronegativity values. En is short for electronegativity. They're on the back of the periodic table. Okay, so if I say, what type of bond is this? You're going to go to your periodic table, you're going to turn it over, you're going to look up your electronegativity values, 2.5, 4.0. You're going to subtract them. 4.0 minus 2.5 gives us 1.5. So great, we have a number. What does that number mean? Anyone remember meaning? You don't remember what it is. Okay, that's why I'm summarizing it here again. Okay, so once you have your number, this is where you need to know those ranges and what they stand for. I'm going to simplify it so it's easier for you to remember. Ionic is greater than 2. Nonpolar is less than 0.5. Polar is everything else. Okay, so where would 1.5 fall, Katie? Polar. It's not below 0.5. It's not above 0.2. Okay, so this is a polar bond. All right, let's move over to molecules now. We just did this, so this should be a little fresher. Molecules refer to our Lewis diagram. So you have to have a Lewis, whoops. You have to have a Lewis drawing. In order to figure out molecular polarity. Okay, this is not a mathematical thing. It actually is. If you were in honors, we would make you do all the math here. But here we can just visualize this and say if it's polar or not. So if something is polar, what is true about the molecule in terms of the things around the central atom? They're not equal on all sides, or something is different. So I'm just going to put different here. Okay, not the same. And then we have non-polar, where things are the same around the central atom. Okay, we do not have an ionic option here because we're only dealing with Lewis structures for covalent molecules. All right, so just be aware that depending on what you're asked to do, you either need to do math or say polar or non-polar based on the shape. All right, any questions on that? Okay, how much time did we have yesterday to work on this stuff? Where were we in terms of the packet? I know some people are a little further than others. Most of you have at least started page 10. Okay, some of you may not be done with it. The only thing you weren't able to do up today is the last column. Okay, so for whatever part of that you have done, go ahead now and answer the question in the last column. Okay, remember, use your polarity of your molecule to determine if it will dissolve in water. That should be a very easy yes or no. And I'll give you about 5 minutes to work on that. We'll go over one together so everyone is sure. And then we will move to naming. Okay, let's just go over this one real quick to make sure everyone's good. What type of molecule is this, polar or non-polar?
Polar, because it's a.
Polar, because something is different.
How do you
My
not see
my
it?
head was in the way, right? Okay, so this is polar. Will it dissolve in water?
Yes.
Yes.
It will.
Anything polar? Yes, will dissolve in water. Okay, so anything polar dissolves in water, anything non-polar isn't. Would it dissolve in oil?
No.
You're right. I have to think through that one for a minute. Sorry. No, would not dissolve in oil. Okay. And the reason I'm moving a little quicker is today, just in case we have a snow day tomorrow, I would like to get as far as we can. So I hope so, but I don't know. Weather is finicky. All right, we are skipping intermolecular forces because it's really not that important. You did hydrogen bonding in biology anyway, even though you don't remember it. And then the bottom part was what we just did with like dissolved light. So that brings us to part B of the packet on page 11. All right, so all along we have been referring to these compounds just by the letters CH4, NH3, H2O, which we know is water, but that is not the true name of H2O. H2O has a scientific name called dihydrogen monoxide. Okay, so water is just a common name that we call it, but this is its real name. So there is a language, just like Spanish. We count differently in Spanish, we count differently in science, and we name things differently. So we're going to learn how to name compounds. Let me pull up the PowerPoint. So there is a new PowerPoint added to your Google Classroom that I'm going to show you here on the screen, but if you do need to go back and reference it, it will be in there. Okay, so first of all, the naming that we are talking about here, whoops, it would help if I put that on the screen. The naming we're going to talk about only refers to covalent compounds. Okay, so anyone remember what makes something a covalent compound, like in terms of where the elements are on the periodic table? Does anyone remember what makes something, what types of elements are in a covalent molecule based on where they are in the periodic table? What types of elements? Okay, we have a non-metal bonded to a non-metal. Okay, so the naming we do now is going to be different than the naming we do in the next chapter. This only applies to covalent compounds, two non-metals bonded together. Okay, so the rules we give you will only be for this type of compound. All right, so we've been working with chemical formulas. We know that when we are given a chemical formula like H2O, that means that we know how many atoms there are of each type of element. This tells me that I have hydrogen. This 2 means that there are 2 hydrogen atoms and 1 oxygen atom. Okay, so that is why we draw water with 1 oxygen and 2 hydrogens. And when we draw a sluice dot structure, we use those ratios. Okay, so that is very important in naming of molecular compounds. We're going to skip the table at the top for a moment. Okay, you can also cross out the first bullet in your packet because we're going to skip that. When we write the name, I'm going to move this down so you can see it. When we write the name of a covalent compound, there's a couple of rules we're going to follow. First of all molecular compounds will end in IgE. Also, the name is going to tell you the number of atoms in the formula by using prefixes. So here's a prefix, here is a prefix. We will learn that di means 2 and mono means 1. You are going to need to memorize these prefixes, but most of them are ones you use in geometry, like tri for triangle or penta for pentagon. Okay, so whoops, I'm going to skip that for a moment. Here are the prefixes you need to memorize. 1 is mono, 2 di, 3 tri, 4 tetra, you can read, 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, and dexa. Nona and hepta might be ones you haven't heard before because we don't often have 7-sided and 9-sided figures. Does anyone need more time on that? Okay, additionally, because we are going to have to change the ending to our name to "ide," you need to know how we can change the names of our non-metals to end in IDE in case you need to use that. So this is not included, but you can use it in the space next to your table there. You're going to want to list, whoops, you're going to want to list these. Okay, I'm going to write them over here so you can see them a little clearer. So first of all, hydrogen is a non-metal, but instead of hydrogen, when we end with it, we write it as hydride. So hydride is our first one. Nitrogen becomes nitride. Oxygen becomes oxide. I will leave these up here, so if you can't keep up, that's fine. Fluorine becomes fluoride. Phosphorus becomes phosphide. Arsenic becomes arsenide. Make a second column here. Sulfur becomes sulfide. Selenium becomes selenide. Chlorine, chloride, iodine, iodide, and bromine is bromide. So the halogens are pretty easy. They all end in INE and they turn into IDE. So chlorine is chloride, iodine, iodide, bromine, bromide, chloride. Some of the other ones get a little trickier because you have to change oxygen into oxide. Right, so you will practice these so you'll get to be better with them, but be aware that these are the way we change them into IDE endings. So have that list handy. Get up there. Anyone need more time to write these? Okay. So now let's get to the naming part. Okay, so just a couple more rules. And then we're going to put it all together. As this is also in your packet under more molecular compound rules. If there is only one of the first element, okay, so for example, carbon monoxide, which is CO. We don't write the prefix mono if the first element only has one, okay, but we do write it if the second element only has one. So it's a weird little rule. Carbon dioxide is another example. Okay, we don't write monocarbon dioxide, it's just carbon dioxide. This part you don't have to worry too much about, and I only put it in here because if you read something, it might confuse you a little bit. Sometimes when the prefix and the name of the element both end in vowels, they will drop one of the vowels to make it sound better. So normally we don't call it carbon monoxide, we just say carbon monoxide. Or sometimes you will hear tetroxide instead of tetraoxide, but either one is okay. So I'm going to just recommend you always leave the double vowel in, that way you don't have to worry about it. There are times you can't drop the extra vowel, like dioxide. If you change that to doxide or dixide, that just sounds weird. It is not the same word, okay? So when in doubt, just leave both vowels in there, okay? I used to really harp on this, but honestly, it's really not a big deal, so I will not mark it wrong if you leave the double vowels in, so just keep them there. All right, so now you will also notice that the name of the first element does not change. We don't change the ending, only the ending of the second one. Just have a couple minutes left, so I think we will stop there. If we don't have class tomorrow, we'll finish this up in 10 minutes on Monday. If we do have class tomorrow, we're gonna have lots of time.